Our next speaker is Miri Kenig, who is also a PhD student in the School of Physics, and she will talk about GenAI for quantum reality, from learning to discovery. Okay.
So we're going to be talking about GenAI for quantum reality, but let me start by telling you why. Why GenAI? Why for quantum reality? Because we hear a lot about GenAI, especially since ChatGPT, DALL-E, Deepfake, Sora, and others came into our lives. GenAI refers to models that are trained to understand patterns and distributions within a given data set. But unlike traditional AI models that are designed for specific tasks, GenAI are built with the capability to produce new, previously unseen content autonomously. And this paradigm shift in AI has opened up a realm of possibilities across various domains. It can be used in any part of our lives: finance, healthcare, cyber, law, etc. The possibilities become endless. As a physicist, I was curious to see if this magic could also work for science. If GenAI can understand quantum physics the same way it understands language or faces, just imagine the power of such a super intelligent mind that can learn by itself much more than any human being, never gets tired, and can acquire unlimited multidisciplinary knowledge. It would be amazing, but more than that. I want to tell you something about why specifically GenAI. What makes it unique? What makes it stand out from all the other machine learning models? And I will tell you this. GenAI is not constrained to our knowledge. It understands the data independently and allows us to explore the unknown from the unknown. And let me explain what I mean. Imagine the realm of knowledge. It can be divided into three sections. Section A is what we know we know. We know that 5 times 5 equals 25. We know our objects move in space and time. When you drop a ball, it falls to the ground due to the force of gravity. There is no question about it. Here we hold all the things we have a clear understanding of. Section B is what we know we don't know. We don't know how to solve all differential equations analytically. We are aware of the gaps in our knowledge, but we might have an idea of how to address them. Section C is what we don't know we don't know. Before the discovery of electricity, people didn't know. They didn't know about it. It wasn't even a possibility. This represents the unknown, where discoveries exist outside of our current awareness. In general, most of scientific research works in a way that aims to move us from B to A, from areas where we recognize our lack of knowledge to areas of clear understanding. We study the things we know we don't know enough about. In cybersecurity, for example, defenses are developed based on known threats and vulnerability. What is special about GenAI is that it offers two key features. First, it autonomously understands the data and identifies the patterns independently, reducing reliance on human understanding. Second, it generates new content by detecting what can change and what cannot, allowing a new way to explore and analyze data. These capabilities of GenAI may pave the way to a much higher level of scientific insights because it allows us to work from the C area. So my goal today is to show you what we have found and learned in this context from applying GenAI to quantum problems. Okay? GenAI learns by a process called training. During the training, it is fed data sets containing examples of type it is supposed to generate. After the training, it can produce new examples based on the patterns and features presented in the input data set. in order to test the performance in terms of the physics, we compare the GenAI results to the expected results from non-physical formulas. In the following, I will show exactly how. Let's get started. Let's dive into the physics and describe the general problem we're talking about. Here's a classical works example as shown by the Galton's board. The Galton's board is a device that demonstrates concepts from probability theory. Imagine a ball falling through a series of pegs, randomly deflecting left or right at each step. By repeating this process again and again, many times, and observing where the balls collected the bottom, we can see the probability distribution of all the possible positions for a ball that falls through this medium. For classical particles, such as balls, the result is the Gaussian probability distribution, meaning that the highest probability of such particle is to end close to where it started. We can look at this device as a model for a physical problem and divide it into three parts: an initial state, a problem, and the solution. The initial state is where the ball starts from. The problem is the properties of the medium. The solution is the statistical final positions after some time t. As for the medium, it could be an orderly medium with, for example, a specific distance between the pegs, or it could be a disordered medium where the peg's position is chosen randomly or with different probability of jumping left or right. Now, let's move to the quantum and explore the same experiment, only now with a quantum particle. Okay? So what will be different? As a quantum particle exists in a superposition in multiple places at the same time, instead of choosing to deflect left or right, it deflects both, left and right, simultaneously. Quantum particles exhibit wave-like behavior. They go through many different paths at once and lead to interference effects, which means the path can either enhance or cancel each other out, interfere constructively or destructively. That, of course, influences the final probability distribution. Two key differences from classical distribution. First, the highest probability is not to remain close to the origin, but to finish far from the starting point. And second, and even more important, the width of this distribution, the speed at which the particle is spreading through the system, is much faster. Quantum particles spread linearly with the number of steps, whereas the classical particle is spreading only as the square root of the number of steps. This may give you an intuition of the potential speed of quantum algorithms based on those quantum walks. We are going to do this again and divide it into three sections, three parts: an initial state, a problem, and the solution. The initial state is where the quantum particle starts from. The problem is the properties of the medium, orderly or disordered, and the solution. Okay? Now that I've explained to you conceptually, let me take you to the simulation. As you can see here, the picture looks a little bit different. We've replaced the pegs with channels, and you can notice the wavy behavior. The colors represent the probability of finding the particle. Yellow indicates a high probability of finding the particle, and dark blue 0. All the shades in between accordingly. In our study case, we've taken it a step further. Instead of one entry site, now we have 10 with different depth. It's called a lattice. You can imagine it as a chain of 10 potential walls with different energies on each, so that it defines a disordered medium, because the deflect probability for each site is unequal. It's chosen randomly. Okay? So for each site, higher energy means a deeper wall, which means it will be harder for the particle to get out and deflect left or right versus a site with low energy. Okay? Each set of energies defines a problem as a new scenario for the properties of the medium. Different problems lead to different solutions, of course. In addition, we had another particle. The particles jump between the sites as they move between the pegs. But when more than one particle is involved, we get non-classical correlations, dependencies between the particles' position as time passes. Their wave-like behavior causes mutual interferences that make them depend on each other. As a result, the solution must hold the information on both particles. Okay? So how can we do that? For that, we have the correlation map. The two-particle correlation map represents the dependent relationship between the two particles. Again, the shades in between dark blue and yellow indicate the probability of finding the particle at that position. So for example, in this specific scenario, there is a high probability of finding one particle at site 6 and the other at 7, or the opposite, the first one at site 6 and the second on 7, versus finding them on the sites 5 and 4. For each initial state and the set of energies that defines the problem, we will get different correlation map as a result. Now, let's move to the dataset creation. As I mentioned, the idea is that the GenAI receives a set of examples, learns them, and then can generate new data based on the patterns it has discovered. So we start with a specific initial state in which the two particles are placed at two adjacent sites in the center of the lattice. We input into the GenAI set of images, each representing both the problem and the solution at the blueness level. This means the bluer the shades, the higher the probability. Okay? The problem is what you see on the left part of the image. It's 10 values, random energies for 10 sites that defines the disordered medium. And the solution is all the rest, is the calculated correlation map after some time t. Okay? We created a few data sets with varying levels of interactions between the particles, none, medium, and strong, and trained the GenAI on different scenarios of the disorder. Okay? The results shows that GenAI successfully learns the physical rules and can generate new pairs of random problems together with the physically right solution. Here we can see that as learning process progresses, the dimensions, the distributions becomes closer to the exact solution. As I already said, we evaluate the GenAI performance by comparing the solution from the GenAI to the expected solution from theory. And this basically indicates that the GenAI can correctly interpolate the physics. Okay? Extending our testing to other data sets, as you can see here, no interaction, interaction-free, and strong interaction, we can confirm that GenAI manages to capture the complex dynamics of the quantum particles. After seeing that it can physically reproduce our expected solution, the GenAI also managed to identify by itself the level of the disorder as a relevant parameter of the problem and enable us to manipulate it. By doing that, a physical phenomenon called Anderson localization was revealed. It is a change in the particle's behavior depending on the level of the disorder in the system. What makes it interesting is that although Anderson localization is well known in quantum physics, it was not introduced to GenAI. In fact, it can be concluded that if we were not aware of this phenomenon, GenAI would have discovered it for us. This, above all, is a proof of concept that GenAI allows us to work from the C area, from the unknown, and discover physical insights on the data. We decided to take it a step further and tested the GenAI ability to learn the full two-particle problem If you remember, what I've shown so far is dealt with the problem of two particles with a specific initial condition. Now we consider all possible initial states, and instead of the correlation map, now we have this complex matrix that represents the full solution. The full solution contains the magnitude and the phase of the complex valued matrix that represents the whole solution for two particles arranged at 10 sites. Again, we have created several data sets with different levels of interactions and trained the GenAI. Here we also received excellent results. Looking only at the magnitude solution, we can see that as learning progresses, the images become similar to the expected solution. Okay, amazingly, we found that also here the GenAI identifies the disorder level parameter and reveals the Anderson localization. Okay, the next step was to test whether the knowledge accumulated. This figure shows that a pre-trained network can accelerate the learning of new and even more complex problems. While the blue network learned the case of two particles with a medium interactions, starting from scratch, the red network built on the knowledge of the blue one and learned the propagation of three particles with strong interaction. It's easy to see that it learns much quicker. So what we can understand is that it is enough to teach each type of problem only once because the knowledge accumulated. Okay, now let's summarize. The remarkable advancements in GenAI create opportunities to explore and analyze data in a way that we were not familiar with before, in a way that is not constrained to our knowledge or understanding. I studied the ability of such models to learn and explore correlative quantum dynamics. The algorithm I presented here proves that GenAI can learn quantum processes and discover physical insights on the data. It managed to learn a non-trivial set of quantum problems, identify the relevant physical parameter, enabled post-training controlling of it, and finally revealed an underlying physical phenomenon. Adding to the fact that the knowledge is accumulating and that it only gets smarter, the potential is huge. With this knowledge, we have entered uncharted territory, and we can begin to apply GenAI to unsolved physical phenomena. Hopefully, in the future, GenAI will be able to assist in the early detection of diseases such as cancer based on subtle changes in medical data that might not be obvious to human clinicians. GenAI is truly one of the most intriguing fields when considering the vast spectrum of its possibilities. It is so exciting to be here in this fascinating era where GenAI encourages you to think beyond the obvious and execute creative ideas. Thank you very much for joining me.